Um, Hello everyone, welcome back to the DDLC seminar series. And today it's an honor to present today's speaker, and it's Professor P.R. Kumar from Texas A&M University. And today's talk is gonna be about exploration versus exploitation, from adaptive control to reinforcement learning. And before we begin the talk, a little bio about Dr. Kumar. And he did his undergrad in IIT Madras and his doctorate in University of Washington. Then he started as a faculty member with the math department at the University of Maryland. And then he moved on to the ECE and CSL department at UIUC. And then from 2011, he's been with Texas A&M University. He has worked on a number of problems. There's game theory, adaptive control, simulated annealing, machine learning, queuing networks, manufacturing systems, scheduling water fabrication plants, wireless networks, and network information theory. And currently, his research focus includes renewable energy power systems, security, automated transportation, traffic management when it comes to unmanned aerial vehicles, the millimeter wave 5G, and cyber physical systems. He's a member of the US National Academy of Engineering, the World Academy of Sciences, and Indian National Academy of Engineering. He was awarded an honorary doctorate by the Zurich, and he received the Alexander Graham Bell Medal of IEEE and IEEE Field Award for Control Systems, also the Donald P. Ekman Award of American Automatic Control Council, also the Ellersick Prize for IEEE Communication Society, the Outstanding Contribution Award for ACM Sigmoville, the Infocom Achievement Award, the ACM Sigmoville Test of Time Paper Award, and ComsNet's Outstanding Contribution Award. He is a fellow of IEEE, ACM, and IFAC, and he is an honorary professor at IIT Hyderabad. And without much ado, I'll pass over the mic to Dr. Kumar.
Thank you very much, Nishant. It's a great pleasure to be virtually at Cornell. The last time I visited was many years ago. Let me share my screen. Can you see my screen?
Yes, I can see your screen.
Nishant? Yes.
Yes, I can see
it.
it.
I'm going. Now, the whole screen?
Yep.
Okay, all right. Okay, so I've worked with a number of people on the kinds of problems that will be talking about, but I want to highlight the first person here. Can you see my cursor, by the way? Cursor?
Yep, I can see your cursor.
Wonderful, okay. So the first person I worked with was Arthur Becker, and Art came up with this beautiful idea that I will talk about. And so he was one of my first PhD thesis students. And okay, so let us move on. So I'm going to talk about two themes in learning, MDPs and linear systems. So let me start with Markov decision processes. So I'm sure all of you know what a Markov decision process is. There are a bunch of states, these circles called which constitute the state space. And there's a bunch of actions. The set of actions is denoted by U. And if you are in state I and you take action U, then with a certain probability, you go to another state J. And for that transition, you get a certain reward. The reward depends on what state I you're in, what action you took, and what state you went to. Now, these transition probabilities are unknown, so we parameterize them. So we suppose that they depend on an unknown parameter theta, and theta belongs to some set of parameters. Okay? And now for every theta, every possible parameter, if you knew the parameter, then you know the entire Markov decision process, and you can determine the optimal policy. And the optimal policy is a stationary policy. What's a stationary policy? It's a mapping. Well, it's a mapping from states to actions. For every state I, it tells you what action to make. And so this optimal policy is a function. Okay. Of course, it depends on the parameter theta. Now, there is a true parameter theta, which I'm going to denote theta 0, let us say in the set capital theta, but we don't know what it is. So it's an unknown system. And our goal is nevertheless to maximize the long-term average reward. So this is the reward that you get at time t. You sum it up from 0 to t minus 1. This is the total reward you get in capital T steps. Divide by capital T. It's the average reward over the first t time steps, and then you take the limit. So that's the average reward over an infinite horizon. And the system is operating under the probabilities corresponding to the true parameter. But as I said, you don't know them. But nevertheless, you want to maximize that. Now, suppose we did know theta 0. If we knew the true parameter, then of course, we would just apply the action given by the optimal policy for the true parameter, but we don't know theta 0. Okay, so how should we proceed here? So we are going to take a certainty equivalence approach. And this was first analyzed by Peter Mandel at Charles University in the then Czechoslovakia. Okay. So what is certainty equivalence? We're going to estimate theta 0. We don't know the unknown parameter, so we will estimate it. Okay. And in particular, we'll estimate it by, let us say, a maximum likelihood estimate. What is that? Because this is Markovian, the probability of a certain trajectory is given by the product of the transition probabilities. So the maximum likelihood estimate says choose that theta under which these transition probabilities are most likely to have happened. So that's called the maximum likelihood estimate. Then what certainty equivalence is that then you choose an action that is optimal for that estimate. So you just pretend that that estimate that you made is the correct, and you choose an action. Okay. So if the estimate is theta hat t, you take an action ut, which is optimal for that estimate when you're in that particular state. And the questions that you'd like to ask are, hey, is it true that the parameter estimates you make will converge to the true parameter? But that's a very strong condition. And you may be satisfied with something lesser than that. You may say, I don't really care whether the parameter estimates converge, but the control law I'm applying should converge to the optimal control law. And this is called self-tuning. And Mandel was the first to examine this. And he showed that, yes, this will happen provided a very, very strong identifiability condition holds. What is that identifiability condition? It is that no matter what two parameters you choose, not what two parameters you consider, and no matter what state you're in and what action you take, the outgoing transition probabilities are different. So in every state, whatever action you take, you get information, enough information to discriminate between two parameters. So you're always able to distinguish parameters, okay? But that's a very, very strong condition, and it doesn't even hold in the bandits, in the case of bandits. So for example, in a bandit, if you play a certain arm, all you learn is something about that arm, but you won't learn anything about other arms. So if you have two different parameters which differ for the other arm, you're not going to learn anything when you play a different arm. So this identifiability condition is way, way, way too strong. Okay. So what happens if the identifiability condition does not hold? And that was considered in the PhD thesis of Vivek Borkar, who's at IIT Bombay, and in his PhD work with Praveen Varaya. And he said, no, there's a fundamental closed loop identifiability problem. So what is that? So when the identifiability condition doesn't hold, your parameter estimates will converge to some random theta star. They'll converge. And let's say the control law also converges. Okay. This will happen if the parameter set is discrete. Let's just suppose the control law also converges. Then what happens is, as the parameters begin to converge, you stop exploring other control laws because you're converging to one control law. So you stop exploration. So that means eventually the system looks like this. The transition probabilities are given by the true parameter, but the control loop is being closed under the policy corresponding to what you think this parameter is. So the system, after some time, is actually evolving like this. And you're not exploring new controls here. So this is actual closed loop system. But what you think it is this. Because you know that you're closing this control law, and you believe that the parameter is theta star. That's the estimate you've made. And you're happy with that estimate only because this configuration coincides with this configuration. So if these two coincide, then you cannot distinguish theta star from theta 0. And that's why you can converge to a theta star. So this is what the estimator thinks it is. And under any good estimator, they would have to be equivalent, or you change your estimate. Okay? So that's what you converge to. And that is called closed loop identification. So you determine the transition probabilities from I to J under a particular action, the action corresponding to theta star. So you can determine those transition probabilities, but only for certain actions, not for all actions. And you're not exploring all actions, so you don't know whether there is something better out there. And unfortunately, this limiting policy, this is not optimal. Okay, so that's this whole exploration versus exploitation dilemma. As you converge, your exploration stops, and you lock yourself into a suboptimal estimate, and you don't learn anything more. So how do you overcome this? And this was examined by Art Becker, whom I mentioned earlier. Was one of my first PhD students. And Art came up with a beautiful, beautiful idea. He said that there is a bias that this maximum likelihood estimate has. And if we can undo that bias, then we can fix the problem. So let me explain that to you. Let V optimal theta be the optimal reward attainable if the system parameter is theta. What's the best that you could do if this was a true parameter? Okay, let that be the optimal value function. Now, these two configurations are equivalent. Now that has a consequence. On the left, this policy is indeed optimal for theta star. So this system is running optimally for the parameter theta star. That means the reward that this system incurs is actually the V optimal of theta star, because this is optimal for this. However, on the right-hand side, this policy is not optimal for theta 0. So the reward incurred by this configuration is less than or equal to what you could get as the optimal reward for theta 0, because it is suboptimal. Okay. However, these two configurations are realizing exactly the same reward because they're equal. Okay, the transitions are equal. Therefore, this quantity is larger than this quantity because the two rewards are the same. So that is the fundamental bias that the certainty equivalence has. You converge to a policy theta star whose optimal reward is less than the optimal reward for the true system. So you don't go to a parameter with an optimal reward larger than that of the true system. You only go to something with a smaller reward. In particular, this is what you get. The optimal reward for theta star is attained by the optimal policy for theta star applied to the parameter theta star. But by the closed loop transition probabilities being equal, this is the same as the reward that you get when you apply the policy for theta star to theta 0. But this is less than the optimal reward that you can get for theta 0. So this is larger than this. Now, if you can make this smaller than this, then you'll get equality throughout. And then this optimal policy for theta star will also be optimal for theta 0. Okay? So ultimately, what you want to do is you want to bias your estimate to favor thetas with higher V optimal so that you converge to a parameter with a higher optimal reward. So you want to prefer parameters with a higher optimal reward that could be attainable if they were the true parameters. Okay? All right. So we will reverse bias it to prefer that. Okay, we'll try to reverse this bias that maximum likelihood intrinsically has. So I'm going to bias a maximum likelihood estimate to favor parameters with larger rewards. That's the goal. Okay, so this is the standard maximum likelihood estimate. At time t, you'll choose a parameter theta, which explains the past t transitions well. Okay, now I'm going to put a bias in favor of parameters theta with a larger V optimal. But I'm also going to raise it to a power alpha of t. Okay. So I am biasing it in favor of parameters with larger V optimal theta, but I'm also adding alpha t. And the reason to add alpha t is that you need a delicate balance. Okay. I need this bias to be large enough that it moves, it actually affects the maximum likelihood estimate and moves it to parameters that have a larger reward. So in other words, this thing should kick in. So I need a large enough weight here. But at the same time, it should be small enough that it doesn't damage the maximum likelihood estimate, because you do want it to estimate the transition probability. So you just don't want to completely damage the maximum likelihood estimate. So you need a delicate bias, okay? And what we will choose is we will choose an alpha which goes to infinity. As t goes to infinity, it will go to infinity. And that is to actually nudge it towards parameters with a larger reward so that it has an actual effect. But you don't want it to be too much. You want it to be little of t so that you don't lose the good properties of maximum likelihood. Now, what is a parameter, what is an alpha t sequence that is little of t but still goes to infinity? For example, log t. Log t goes to infinity as t goes to infinity, but it's little of t. Square root of t is also such a function. So you have to choose your weighting parameter, alpha t sequence properly. And how to choose it depends on the context. It may be different for Markov chains, from linear quadratic problems, etc. Okay. Okay. So here's a theorem. Okay. And the theorem is, we're going to call this reverse biased maximum likelihood estimate. It chooses a parameter which maximizes. Here I've just taken the log of the previous criterion. Okay. Instead of maximizing the likelihood, I'm maximizing the log likelihood, which is the same thing. And I've taken the log here. So what was in the exponent comes here as a multiplier. So you want to maximize the reverse bias maximum likelihood estimate. And then you follow it to certainty equivalence. After you make an estimate, you choose the control that's optimal for that estimate in that state. And the theorem is, then the long-term average reward is optimal. What's the long-term average reward? This is the reward you get at time t. This is the total reward over t steps. This is the average reward over 2 steps. You take the limit. That's the long-term average reward. That will be the actual reward that could be obtained for that true parameter. Okay, it's optimal. Now, note one thing. What we are doing here is we're taking the total reward for t steps and dividing it by capital T to get the optimal long-term average reward. Okay. And this basic idea of reverse biasing was explored in the period 1980 to middle of 90s. So we examined it first for finite states and actions, finite states, but general parameter sets. Then we also explored for LQG systems, then nonlinear systems, and then even for controlled diffusions. Burkhardt looked at it, Ty Duncan looked at it, etc. So this is what happened in the last 2 decades of the 20th century. But all of it for long-term average reward. And in fact, in the control field, people at that time were mainly fixated on things like long-term average reward or discounted optimality or something like that. Okay. Then there's a more stringent notion called regret. So regret is a finer measure of performance than long-term average, and it was introduced by Lai and Robbins in 1985. So what is regret? Regret says don't just divide by t and take the limit. It says actually look at the total reward you get, compare it to what you could get. So this is the difference between the total regret up to time t compared to the total regret that you could get in expected value if you knew the parameter. Let's say it's a 2-arm bandit problem. There are 2 parameters and you choose the maximum. So I'm defining this regret for the case of a bandit, okay? And long-term average simply says that if you divide this by t, it goes to 0, okay? So long-term average optimality corresponds to saying regret is little of t. But Lai and Robbins asked a much stronger question. How small can you make regret? How small can you make this grow? And they gave a beautiful answer to this problem. They showed that this optimal regret, the optimal rate at which grows is log t. And not so basically this grows like log t. And not only that, they said that the asymptotic constant is related to the Kullback-Leibler information. Okay, so they actually characterized the asymptotic optimality of regret. Okay? And all we had done was just show that this is a little of t, but they said, let's try to get asymptotic optimality of the regret. Okay? And they also came up with a beautiful policy for doing that, which I'm going to illustrate in the case of bandits. Okay. Now, I assume every one of you knows what bandits are. There are 2 slot machines. Each slot machine has a probability of success. Let us say slot machine 1 has a probability of success theta 1. Slot machine 2 has a probability of success theta 2. And you want to pull every day you have to pull one of the bandits. And if you choose, and obviously you like to choose the bandit with a larger theta, but you can come, but you're learning as you go along. So you keep playing arms, and you can look at the regret. How much did I make over the last 3 days compared to how much I could have made? Okay. So Lai and Robbins came up with an optimal policy, which actually is asymptotically optimal. And this is called an upper confidence interval policy. So what they said, so let us suppose there are m bandits, okay? For each bandit, draw a confidence interval. So if I've played 100 times and I've gotten 70 successes, then I'll draw a confidence interval around 0.7, right? So draw a high confidence interval for arm 1. This is for arm 2, arm 3, arm 4, arm m. So for each bandit, you draw a confidence interval. Now they said, now by the way, the length of this confidence interval will be large if the uncertainty is large. And the uncertainty is large if you haven't played it much. So if you haven't played an arm much, its confidence interval is large. But its confidence interval is also high if the mean is high. If this is a very good arm, then let us say that this is a very good arm, then H1 will tend to be high. But H2 could be high because you haven't played it, not because it's good, but just because you haven't played it. And what they said was play whichever bandit has the highest higher endpoint. So look at H1, H2, H3, etc., and play whichever is the largest. And that's called the UCB, upper confidence bound policy. And they showed that that actually attains this optimal regret asymptotically. Okay. Now, why is that? The intuition is the following. The upper endpoint will be large if either the arm is good, if the mean is large, it will be high, or if it has not been explored enough, then the uncertainty is large. So basically, this trades off good performance versus not enough exploration. So it balances exploration versus exploitation in an asymptotically optimal way. Okay? And this is called the UCB policy, and everybody in reinforcement learning knows it. Note one thing though, this is asymptotically optimal. That is in the limit. Now, one other question that you ought to consider is how large should T be so that these two are approximately equal? Okay. And in fact, it turns out that T has to be extremely, extremely, extremely large for this to happen. But something else, in the transient period, you can actually make this left-hand side much more than the right-hand side. Okay, so there are policies which in the transient case will beat this tremendously. Okay, and we'll see that. Okay. Now let us consider the biased maximum likelihood policy for a variety of contexts. Let's look at the multi-arm bandits case. In fact, we look at the exponential family of bandits. So this is a class of the bandit reward probability distribution is given by this class, and theta is an unknown parameter. A theta is like a normalizing constant, which turns out to be strictly convex. X is the outcome of the bandit. Okay, and the expected value of this single parameter exponential family is the derivative of A prime. It turns out A is strictly convex, A prime is strictly increasing. And the reward bias maximum likelihood estimate simply says this is the likelihood ratio, right? If you play the arms, then this is the probability of getting a success. This is the product of the probabilities. And what you're biasing is, it turns out that the mean reward and the maximum of the mean reward is the optimal reward, right? That you have to bias. But you can actually choose any monotone function of the optimal reward also, because all you want is an inequality. So RBMLE is this class of policies where you can choose any monotone function you like, and alpha t has to be chosen appropriately. And by choosing, and as I told you, alpha A prime is already strictly increasing. So, and this also F is strictly increasing. So you can combine these, and you can also take a logarithm, which is monotone, etc., etc. And then ultimately, you can come up with an explicit policy. Okay, choose any strictly monotone function, and you maximize this criterion, and that gives you an index policy. Index policy means after you play an arm a few times, it has an index. And this index is given by how much reward it gave and how many times you played it. And you simply choose the arm with the largest index. And it turns out that such an index policy is optimal. Okay, you only need to play the arm with the largest index. And I will show you what this index policy is for different classes. Okay, so let us first, this is the exponential family. If you have Bernoulli bandits, Bernoulli bandit means when you play an arm with probability theta, you get 1. With probability 1 minus theta, you get 0. Okay. Turns out that the index, supposing there's an arm, you've played it a total of n times. It has given you S successes and F failures. Then this is the index. Okay. If there's an exponential bandit means every time you play it, it gives a reward according to an exponential probability distribution. Xi is the reward you get on the ith play. Then it is simply this. I should mention here, by the way, you have to choose this parameter alpha, right? So that's over here. In this case, it's over here. And it can grow at, say, log t or something. And if it's Gaussian bandit, so every time you play, you get a Gaussian reward where the mean, say, is unknown. Then the index is very simple. It's the total reward you get divided by how many times you played, plus the parameter alpha. So very simple index policies turn out to be what the reward bias method gives you. But the question is, how does it perform on regret compared to Lie's policy, etc.? So here's a theorem. The theorem is if alpha t grows like gamma t log t, where gamma t is any sequence going to infinity, however slowly, then the regret is O gamma t log t. But we really would like to get rid of this gamma t also. And suppose the gap is known. Gap means the difference between the success probabilities of the smallest and the largest bandits. Then if you choose alpha t to be a certain constant related to that gap times log t, then the regret is log t. But you don't know the gap in general. I don't know the difference between the best and the second best. If they're Bernoulli, Gaussian, or Sub-Gaussian bandits, then we can actually estimate this gap, okay? Because we can estimate probabilities, and then we can adapt to them, and then we can actually get a O log t policy. It adds a little more complexity because you have to estimate probabilities, but that's not a big deal, okay? Okay, how does it empirically perform? So this is, we did 100 trials, and you're going to see the average performance over 100 trials. The time horizon is, 100,000 steps. And there are 10 bandits whose success probabilities range from 0.61 to 0.7 in increments of 0.01. So that's slightly hard to distinguish, separate, okay? And what I'm plotting is the regret versus time. And our policy, this RBMLE, has the smallest regret. Okay. The UCB policy actually is this black line. And UCB actually performs very badly in the transient regime. It's asymptotically optimal, but transient, it's always very bad. There have been other policies which have been proposed. A very good policy is proposed by Ben Van Roy at Stanford called IDS and VIDS. It's a heuristic policy. It's there. Then there's a whole bunch of other policies, KL, UCB, Thomson sampling, which is one of the first person to have actually considered the bandit problem is a guy called Thomson. And he considered a policy which is sampling from the Bayesian posterior. And it turns out to be a very, very good policy, okay, even now. So it's right over here. Then there are, a whole bunch of policies, okay? So anyway, this turns out to be the best. Now, you can also look at the complexity of decision making, because this IDS policy, VIDS policies take a lot of computation, okay? And I'm plotting here average regret versus complexity. So normally I would like the regret to be small. I'd also like the complexity per decision to be small. So ideally I want a policy performing over here in the lower southeast. So this is what's happening. The RBMLE has the lowest regret, and complexity is not too much. The only reason why this complexity is actually a little large is because we're doing this estimation. Otherwise, it would be right over here. Okay. And this is the IDS policy. It's also very good performing. But complexity is, and this is logarithmic scale. So complexity is much, much more. Okay. And there are further statistical properties of the policy. Gaussian bandits. Again, the RBMLE is pretty good. This is UCB. This is IDS somewhere here. It's over here, pretty good. And complexity versus regret. This is good. And this is exponential bandits. Again, it's good. RBMLE. Again, this is UCB. And this policy is Thomson sampling, which is still pretty good. Okay? And complexity versus regret, also good. Okay. Now, we've also studied other contexts, for example, contextual bandits. So in contextual bandits, every day you get a context. And this context could also be generated with an adversary to try to make you look bad. And your parameter is linear in that context, okay, depending on the action you take. And RBMLE, this is RBMLE, it has a regularization criteria. Here, this is the biasing of the mean. This is the data fitting, like maximum likelihood. And this is the regret. And again, you cannot see it over here, but it's pretty good. And and this is the complexity of RBMLE and regret over here. We've also studied Markov decision processes. So I should tell you one thing. So as I told you earlier, we were only looking at long-term average optimality in the 2000s, the last century. But now we're revisiting all this and looking at it from the viewpoint of regret, just because I stopped looking at this adaptive control problems about 20 years ago. So only recently, just a few years ago, started re-examining some of these things because my students came to me and said they want to work on machine learning. Okay, so Markov decision processes. So if the gap is known, that is the difference between the best and the second best policies, then with an epoch-based algorithm, we can get logarithmic regret, okay? And if you plot the performance, so we randomly generated MDPs. So this is a random MDPs with 20 states and 20 actions. And RBMLE's regret is over here. Thomson sampling is pretty good still, okay? And this is a UCRL. UCRL is the upper confidence version for MDPs. Okay, that's how this performs. And if you take random MDPs with 50 states and 20 actions, again, RBMLE has pretty good regret. And this is 50 actions in 50 states. Again, that's very good. We also looked at linear quadratic sub-Gaussian systems. And so we have a standard linear system. The noise is sub-Gaussian, and we'll assume standard conditions and a quadratic cost. Okay. And what we are going to consider, what's inside is RBMLE, but it turns out that for RBMLE, we couldn't prove anything. We ran into some difficulties. But supposing we also constrain the parameters to lie in the confidence interval. So we are combining confidence interval with the bias maximum likelihood. Then we can analyze it. But it turns out that this constraint is never tight. It's always loose. However, I cannot prove it. But putting this constraint theoretically allows us to prove it. Okay, and this is the confidence interval where the log likelihood function is small. Okay. Okay. How does it perform? Performance, it's square root of t, neglecting logarithmic terms with high probability. And there have been many problems which have been studied in the literature. This is supposed to be a model of a Boeing 747. This is a UAV. This is an unstable Laplacian. This is large transient dynamics, etc. And the augmented RBMLE has this empirical performance. Though, as I said, it's the same as RBMLE because that constraint is never tight. Again, in this case also, it's the smallest in the UAV case. And in the unstable Laplace case also, it's very good, and the large transient dynamics. Okay. Now this is a finer examination, and it turns out that the policy closest to RBMLE is something called input perturbation. That's this dot policy. So that's pretty good actually. Okay, and etc. So I'm trying to show you. Well, and these are policies which are pretty good. Okay. All right. Now I want to say something about optimism. Okay. So both the RBMLE, reverse biasing, and UCB embody a principle of optimism in the face of uncertainty. That's actually a pretty good philosophy for life, right? When you're uncertain, be optimistic. As somebody said, the optimist and pessimist, your life will be the same, except the optimist will enjoy life more while undergoing it than the pessimist. Okay. So both of them are optimistic in the face of uncertainty, but they do it in different ways. So what does RBMLE do? It biases the maximum likelihood estimates directly towards arms with larger theta. It directly biases towards optimistic estimates. This is a reward biased MLE. On the other hand, the UCB policy prefers arms for which there's a larger chance of theta. Larger chance of theta because it draws a confidence interval. It tells you the chance that the probability is, the parameter is there, and chooses arms for which there's a larger chance. So both are optimistic in the face of uncertainty, but differently. One is directly, the other is preferring an arm for which there's a larger chance. What's the connection between them? Is there any connection? Okay. Now UCB is actually, this is a primal optimization-based formulation. So UCB first draws a confidence interval. And you can draw a confidence interval by looking at the likelihood ratio and seeing what parameters make the likelihood ratio large. So this is the high end of the confidence interval. And within that, you want to choose the parameter which has the best performance. So that's upper confidence bound. This is upper confidence interval. This is the choosing the best policy in that. Okay. And what does RBMLE do? RBMLE is a Lagrangian formulation. It looks at the likelihood, but adds this Lagrange multiplier. The Lagrange multiplier alpha t times this. I've moved the Lagrange multiplier over here. So this is coming from the constraint. This is a constraint, alpha t, if you multiply it over here, is a Lagrange multiplier, and this is the objective function. So RBMLE is a Lagrangian formulation. This is a primal formulation. And the Lagrange multiplier chosen by RBMLE is 1 over alpha t. We choose that as a Lagrange multiplier, whereas UCB chooses whatever Lagrange multiplier is optimal for the dual. Okay, whereas we directly choose alpha t. Now, how do they compare? So UCB has an implicit Lagrange multiplier. RBMLE has an explicit Lagrange multiplier. How do they compare? Okay, so it turns out we can compare their degrees of optimism. So how close is RBMLE to the centroid of the confidence interval? So the centroid of the confidence interval is the best fit. And if you move far away from the centroid, that means you're becoming more and more optimistic. So the person closer to the centroid of the confidence ellipsoid is less optimistic than somebody on the edge of the confidence ellipsoid. Okay. So we drew the distance of the parameters from the center of the confidence ellipsoid, and RBMLE is much closer to the center. So it's much more conservative in its optimism. But of course, this is just the Euclidean distance to the center. You can actually take the weighted quadratic distance because this is an ellipsoid, right? The ellipsoid has different major and minor axis. So you can actually take the weighted quadratic distance, and RBMLE is actually closer than UCB. Okay? So UCB is perhaps a bit too optimistic. RBMLE is also optimistic, but less optimistic. And this being a bit too optimistic hurts its performance. Now, everybody in reinforcement learning knows about UCB. But what I'm suggesting is a finer degree of optimism. And maybe we're being it too. Maybe we need a RBMLE which is more delicate in its optimism. Okay. Now, the second theme is self-tuning regulators. Okay. So I said I'll say something about linear systems. So the holy grail of control from 1950 onwards was adaptive control. Okay. What's adaptive control? There's an unknown black box. You don't know what it is, but you'd like to hook up some intelligent controller to it called an adaptive controller, and it'll automatically tune itself to the black box and control it optimally. So that's the holy grail of control, adaptive control. Now, early on, it is already noticed by people that control here has two purposes. The control can be used to excite the system, excite the modes of the system so you can learn about it, but you can also control it, that is, steer the system. So control can be used to explore or exploit, or excite it or steer it, okay? And that's why Feldbaum in the Soviet Union in 1960 said this is dual control. He called it dual control. Of course, nowadays we call it exploration versus exploitation. Now, there was a very naive, just somebody hooked up what they called an adaptive controller to an experimental plane in 1967, and it crashed. This was not a rigorous adaptive control, it's just a heuristic. And this is the report on that plane. There are a lot of reasons why it crashed. But what it did was, it brought home one fact central to control theory. The most important thing when you build a control system is it's stable. Performance optimality is secondary. First thing is it's stable, okay? And that's a non-trivial question because the overall linear system becomes non-linear, and trying to prove stability of adaptive controllers kept the control field busy for 25 years. Okay, and I'll give you a brief history of that. So a lot of the action in the starting from 73 was towards self-tuning regulators. So these are linear systems modeled as autoregressive moving average systems, so exogenous inputs, where y is the output of the system. It regresses on itself, and there is these are the control actions, and these are all white noises. Now, this linear combination of white noise actually models colored noise. So if you have a system affected by colored noise, you can do a whitening decomposition and express it this way. These are called RMAX systems, and they are very popular models for process control. Now, most of the controllers in the world are process controllers, which are used for all your chemical plants, petroleum plants, your cars, etc., etc. Now, these white noises cannot be measured. They're just a figment of your imagination, kind of just a mathematical decomposition, okay? And it's widely used in process control. And because you cannot see the noise, it's actually a partially observed system. But the goal in many of these process control systems is to minimize the variance of the output. Why? Because if you're making some product, you want to make it as pure as possible. A big application which influenced this adaptive control, which drove adaptive control, was manufacturing paper. So the way paper is done is you take pulp, and then you have these rollers, and then you you flatten out the pulp, and then you also heat it, and then you get paper. Okay, and there are variations in the thickness of the pulp, etc., vibrations of the rollers. So you want to regulate them to get as fine quality paper as possible. You want the standard deviation of the paper to be as small as possible, because it turns out that people actually sell paper by the guaranteed weight of the paper. So if you reduce the standard deviation, then you can set the 3 sigma limit smaller and save a lot of money. Okay, so this was a big application which drove it, but it was applied to adaptive control of super tankers, ore crushers, etc. A lot of applications of self-tuning regulators. Okay, let me tell you how complex the system is. So let us take a very simple system, autoregressive moving average system. This is, as I said, the colored noise. And now you can write it as a linear system with a regressor phi and a parameter theta with white noise W. But these parameters would be A1, B1, B2, and C1. And the regression vector would be this, and this. But remember, we cannot observe W. So I cannot do standard linear regression. Okay, that's why I'm calling it phi 0. This is the ideal regressor, but you don't know what it is. And these are the two parameters, and you don't know what they are. And if you could estimate theta 0, then the optimal policy, you'd use U to cancel out this, and this. That's what this does. And then ultimately Y would be equal to W, which is the best possible. Okay? But you don't know W. And you also don't know the parameters. Okay? So what you do is you bootstrap. You say, if I knew W, if you knew W, then you could estimate W hat as the error in the regression. And if you knew the error in the regression, W hat, then you could estimate phi. In other words, if you know W, you can estimate phi 0. If you know phi 0, you can estimate W. It's a bootstrapping mechanism to deal with the control, with the colored noise. And you could fit a linear regression to this estimated regressor. And then after that, you could, so ultimately, you get a very nonlinear system. This is your system. These are your least squares are actually gradient estimates. Very, very nonlinear, 1 over R, phi, this is squares, etc. And then you choose your optimal controller, which depends on your estimates, etc. So, can you prove the stability of the system? And this kept the field busy for about 20 years. So I'll tell you what happened. So when this is bootstrapping method work, and that problem was first solved by Lennart Ljung in Sweden in his thesis, he identified a certain condition on the C polynomial called a positive real condition. He could not give a rigorous proof, but it's a beautiful analysis of, we're using something called the ODE approach to analyze stochastic systems. It's like averaging, okay? And the stability and self-optimizing was rigorously proved by Goodwin, Ramage, and Keynes in 1977. The self-tuning property, that is the parameter estimates to converge to minimum variance controllers, this was proved by us a few years later. And then for the gradient estimate and for the least squares estimate, which is much more difficult, a few years after that. Okay. But then something else came along in the 80s. People said, hey, wait a second. All of you are assuming that the true system can be modeled by a second order or a third order or a fourth order system. But that's never really the case. There's always unmodeled dynamics. If you take a beam of metal, it can resonate at multiple frequencies, infinite number of frequencies, infinite number of modes. It's actually a distributed parameter system. So if you model it as a second or a third order system, that's only an approximation. What happens if there are unmodeled dynamics? And these people from MIT shook up the field by considering a system which is nominally modeled by a first order system, but they added some high frequency dynamics and showed that the adaptive controllers, which had been proven to be stable and so on for this dynamics, were driven unstable by a small amount of unmodeled dynamics. Okay? So that launched a whole field into investigations of robustness, and ultimately robustness was proved by various modifications that were done. Okay. So what kind of a theorem comes out when you do this robustness? And it's actually a very, very Baroque theorem. So we say we take an adaptive controller, and then we say that it's optimal when the system is ideal, when the system is minimum phase, the bound on the order system is correct, etc., etc. Then it self-tunes to an optimal thing. It's also stable if the noise doesn't satisfy this positive real condition. And it's also mean square stable if the system is not finite dimensional, but infinite dimensional in a small neighborhood of the finite dimensional system in some topology called the graph topology. Okay? And it also continues to stabilize the system when the adaptation gain is non-vanishing. In practice, you never reduce the learning to zero. You always keep it alive because system could always change. And this proves it's stable even under that condition. Okay, so that's a kind of a Baroque theorem on robustness that was proved in the late 80s. And now we've re-examined this problem and we've looked at finite time performance. As I said, we're concerned now about regret and things like that. And there was a certain algorithm that we created. And then we can actually show that the regret grows logarithmically, even in the self-tuning regulator case. And we also examine the transient performance. So this is the algorithm that we created is called PS, and it has the best regret in several examples. And the estimation error, however, is not the best. Okay, but the goal is not to estimate the parameters. The goal is the transient dynamics of the system should be as small as possible. Okay, and that's what we achieved. So let me conclude. And there were lots of adaptation algorithms that were studied in the 20th century. And currently, there's been a re-examination of these learning schemes from the viewpoint of regret. And the reverse bias method that we studied in the last century actually does very well compared to all the modern stuff. Has provably good theoretical regret performance, seems to have empirically good regret performance, requires low computation per decision. And what about the future? I think if you make it easy to test reinforcement learning systems at scale, then I believe if the applications could take off, then this field also could really have the exponential growth that we've seen in the case of static machine learning. And with that, I will stop. Thank you.
So, thank you so much, Dr. Kumar. We can wait for the questions if they have any. I'll let you know in a minute. Meanwhile, I have one question. So when it just a second. So in the notions of computing these regrets, in some cases, like the contextual bandits, we've considered regularizations, right? And in some cases, the regularization was not included. Like, what?
Oh yeah.
What was the motive behind considering these regularizations or not considering these regularizations?
Yeah. It turns out that previous people who had also worked on contextual bandits had actually had regularization, and the proofs actually work out well when you throw in that term. Okay.
Yep.
Yeah.
Yeah. Because these days,
Well,
recently,
that was the
sorry, yeah.
only case where we did regularization. Of course, like I told you, for the quadratic problem, we introduced the constraint just because we couldn't prove it. And in all the experiments, the constraint was used. But we couldn't prove it without the
Yeah,
constraint.
yeah,
Yeah.
yeah, yeah. I mean, yeah, these days I was just reading some papers like on reinforcement learning, and they consider these regularization terms on proximity of the previous policies to the
Correct.
newly formed policies.
Right.
That I was wondering, like, are there any
Correct.
notions on why these are being considered?
Right. Right.
And there is one question, and the question is: so minimizing regret means optimizing transient performance. Could you elaborate on that?
Oh, yeah, yeah. So, uh, so I forget, but some of these systems may also be, I don't know if they're unstable or not. But there's one problem. Okay, this is a logarithmic scale, okay? So when I say that this is you go from here to here, it's 100 times worse, okay? So basically, the transient jump that occurs here in the beginning, right, is huge, right? And this one is 100 times smaller transient. So the goal here was, you have these theorems which are asymptotic. Even the optimal regret theorem is asymptotic, right? Asymptotic regret theorem. But what you are interested in is, as soon as you connect the system, how does it behave the first 50 steps? Does it blow up and then settle down, or can you even control the transient? And the point is that this transient also is low, as you can see from what's happening in the small time period here. Okay, it goes up to this level and then settles down. Is that clear?
Yeah, if they have a follow up, they'll ask again, and I'll let you know.
Okay.
Yeah.
Okay.
The next question is in slide 31. If I mean, if they understood it correctly, the you said that we use ut minus 1 to cancel out yt minus 1, ut minus 2, and wt minus 1. Could you clarify the step?
Yeah. Yeah. Okay. Okay. So this, for example, could be a model of a paper mill. Okay. And y is the thickness of the paper. U is the action you're taking, and W is the, actually this whole thing is the noise, okay? But mathematical decomposition, you can break it up as a linear combination of white noises, okay? You can think of this as a whitening filter. So this W actually doesn't exist in reality. It's a figment of your mathematical imagination, but you can write the system this way. Now, notice that suppose ut minus 1 is action you take at time t minus 1, okay? Now, definitely you observe yt minus 1 and yt minus 2. So you could choose ut minus 1 to cancel these two terms, right? And you could also cancel this term. This is the effect of yesterday's control on today, the memory in the system. Now, if you could estimate W as you go along, then you can even cancel out yesterday's noise. Okay? So ultimately, you can make yt equal to wt, and that's the smallest possible, because that's white noise. It's completely unanticipatable in the past. So yeah, so self-tuning regulation also attempts to cancel W. Now, how does it cancel W? I'll give you, this is, gets a little bit, if you can follow it, okay? Suppose I could choose UT minus 1, B1 UT minus 1, so that it's equal to minus A1 YT, it's equal to A1 YT minus 1, A2 YT minus 2, minus C1 WT minus 1, and minus C2 WT minus 2. Suppose UT minus 1, and it could cancel all these things. Then YT would be equal to WT, correct? Now, if YT is equal to WT, then tomorrow WT minus 1 will be YT minus 1. So if you, so there's a bootstrapping going on here. If you could cancel out the W's, Y would be equal to W. But if Y is equal to W, then you've canceled out the W's. And you can actually use that. So suppose this was actually W, then what really is entering the system is A1 YT minus 1 minus C1 YT minus 1. Because if this was YT minus 1, move this over to the left-hand side, it would be A1 minus C1. So you can actually cancel UT minus 1 with A1 minus C1 YT minus 1, and that would serve to cancel this and result in Y equal to W, which then self-propagates itself. So there's a lot of tricks like that you can do to handle this W term. Okay. Actually, you don't even need this regressor. It turns out that you could merge this regressor with that, but that's getting further complicated. I will skip. Yeah. Yeah. So handling colored noise was a big part of all of these things. Yes.
I guess there is a follow-up probably, but like the question is, could you please clarify how to handle the Sub-Gaussian noise in your slides?
Oh, Sub-Gaussian noise, we just treat it as a linear quadratic control. Okay, let's just forget, just say it's Gaussian, okay? If it's Gaussian, then you'll get a linear quadratic Gaussian controller, right? Same thing for Sub-Gaussian also.
And could you also elaborate a bit on the confidence region, confidence interval, basically?
For the linear system or for the maximum likelihood estimate?
For the estimate.
For the linear quadratic case.
Yeah.
Okay. So just imagine that this is Gaussian, okay? Forget that, okay? Then xs xt plus 1 minus axt minus but is Gaussian noise, right? And the log of that probability density function will be a quadratic. So this is actually the log likelihood. Except we're pretending it's Gaussian, even though it's sub-Gaussian.
Thank you.
Yeah. So this is the log of the maximum likelihood, and this is the biasing in favor of parameters with smaller optimal cost. Yeah.
Yeah.
And notice the alpha t grows like square root of t in this case, not log t. You remember I told you the Lagrange multiplier. This is one. The Lagrange multiplier is 1 over square root of t.
Yes.
Earlier it was 1 over log t. Okay.
Yeah. Yeah, I think that's all the questions we have for today.
Okay.
Yeah. Yep.
Okay.
Yeah, thank you. Yeah, thank you so much for.
Thank you. All right. My pleasure. All right. Take care, folks. Bye-bye.
Thank you.
Bye.
All right, everyone. Thank you for attending. attending the talk. Hopefully, it was much helpful for you guys. And next week, see you again, I guess. Bye bye.